Hello everyone, this is experiment number 7 where we will look at the application of Hilbert transform. So let's start. First experiment, the first part of the experiment can, uh, looks at instantaneous frequency. Are we able to differentiate between different frequency present in the signal? Okay, so the first part will help us in differentiating different frequency present at an instant in a signal. So let's start. So these are our libraries. We'll be coding in Python. These are matplotlib library which will be used to plot the graphs, numpy library, maths, and the Hilbert. We'll use sample size of 600. Now this is our signal which we made, which is of different, which has different frequency at different in time instants. And here what we did is we took the Hilbert transform of that signal, then we find out the phase present at different time instant in that signal. Then we found out the different frequency, that of instantaneous frequency present in the signal at every instant. And then these are the commands for plotting the things we find out. Let's look at what these looks like. So this is our input signal. It has different frequency. For example, what we gave is 30 hertz here, 60 hertz here, 90 hertz here. Okay, now let us look at the instantaneous frequency find which our Hilbert transform helped us to find out. So these are the frequency which Hilbert transform helped us. This see it separated the different frequency present in our signal. For example, this one is a 30 hertz, this one is 60 hertz, this one is 90 hertz. Okay, the second part of our experiment includes making a signal which is 1 by 1 plus 1 by t square, which is, you know, the signal will something looks like uh, will be a even signal which will be symmetric about the y-axis. And the property of the signal is that it has a maximum, the maximum it attains, the signal attains maximum when the Hilbert transform reaches 0. Okay, let's look at the signal and its Hilbert transform. So this is our signal 1 by 1 plus t square, the green one, and the blue one is the Hilbert transform. So what we can observe is this, that whenever the green attains the peak, the blue one crosses 0. So this could be a unique way of finding peaks where other method fails. Hilbert transform could be very useful in finding peaks. Okay, now third part of the experiment where we'll have an array of these peak signals, and we need to find those peaks with the help of Hilbert transform. Okay, let's start. We'll we'll make the input signal, that is different peaks, by using the random int function present in the. We'll import the random library and we'll make it multiply by different peaks to make the signal uh, look random. Then we'll use Hilbert transform to find out where the peaks are. So this will be a unique way of finding peaks where other method fails, that is, but where methods like zero crossing, autocorrelation function fails. The Hilbert transform might be more useful, as all it does is calculate the zero crossing point of the Hilbert transform. So let's start by looking what this program does. So here we're creating an array of 3000 elements, and here in this loop we are making our array of the input signal, which looks like 1 by 1 plus t square shifted at different times and have different amplitudes. This is this is our initialization for our Hilbert transform, and uh, this helps us in calculating the Hilbert transform. Now what we'll do is plot the input signal and their Hilbert transform, and let's look how does that look like. So let's see. Oh, wonderful! See what happened is the green signals are our input signals, which has peaks here, here, here. Then we calculated the Hilbert transform using, and the blue one represents the Hilbert transform. What we observe is whenever the Hilbert transform crosses 0, the green one attains the peak. So all we need to do is calculate the point where the blue one crosses 0. So we have the peaks of our input signal. This could be used for PPG signal. This could be assumed as PPG signal. The green signals could be assumed as PPG signals, while the Hilbert transform could be used to calculate the peak to peak points, and thus calculating the heart rate.